So on Friday, that was just a general probability packet that hopefully those little videos were good. What today we're going to talk about is some more just basic probability rules stuff. It kind of, the videos in the packet from Friday kind of talked about some of this. So we'll go through it, like complement, mutually exclusive, two-way tables, Venn diagrams, and then you've got like addition, multiplication rule. So we're going to go for that. On Friday, we do have a half day, so we'll be doing one more probability thing and then be done for Thanksgiving break. Yes, ma'am?
I don't think I was here when you got the packet. Yeah, she was here.
On Friday?
No, I didn't come on Friday.
Oh.
Well, we got the package Wednesday, I think. It was right after, like the day after.
You didn't get the
I
notes.
wasn't here Wednesday or Friday.
Gotcha.
Thank you. Yeah, I think I package rolled it. Oh, man.
What? You don't have it? Alright, anyone else see the notes packet? Good.
The one that we got on Friday?
Yeah. Alright, not Friday. It was Wednesday. It says,
How good is Miss
like, how good a free throw shooter?
Because it doesn't matter.
Yeah.
It's talking about free throws. Alright, so we're going to be on the third day of that notes packet. Going from there. So what we're going to do, we're going to play a little game with some rolling some dice here. We're going to watch a little video explaining the rules of the game, see who would win, then we're going to calculate some probabilities, and go from there. Alright, so watch a little, it's like 30 seconds introing this little game we'll play. We'll go for it.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if the biggest number is 1, 2, 3, or 4, player 1 wins. If the biggest number is 5 or 6, player 2 wins. Let's try twice more. Here, player 1 wins. And here is player 2. So who do you want to be? At first glance, it may seem...
Alright. So, the idea here is we're going to play a game. So, I want you to partner up with somebody. We have an even number of people. So, get a partner. And what we're doing is one of you are going to be the player 1 who y'all are both going to roll your dice. So you're both going to roll your dice, and the highest dice is all we care about. Not you're just going to roll and whatever the highest number is. So if the highest number is 1, 2, 3, or 4, whoever is player 1 wins. So y'all decide who player 1 is. And if 5 or 6 is shown, player 2 wins. So decide who player 2 is. Okay. So let's think about who do you think has the advantage.
Player 1.
Go from there. Alright, so what we're going to do is y'all are going to play. Let's do 1, 2, 3, 4, 5, 6, 7. I know, but that'll be good. Okay, let's do that. So let's do it 20 times. So what you're going to do, y'all are going to both roll at the same time, and whoever has the largest number, if it's 1, 2, 3, 4, player 1 wins. If it's 4, 5, or 6, player 2 wins. So y'all make a tally between you two. What's up? Like,
is it both dice, like no matter who rolls the dice?
yeah, so you're both rolling the dice at the same time, and whoever has the highest number, that's the one. The highest number, if it's 1, 2, 3, or 4, player 1 wins. It's not your own dice, it's whoever of the two of you throw the biggest number. That's the one you're looking at. Does that make sense?
Yeah.
You're both going to roll. So let's do an example. I roll my dice, my partner rolls the dice. I roll a 1, my partner rolls a 5. The highest dice was a 5, so player 2 wins. Okay. Alright, so y'all do that 20 times. Tally who wins.
4,
It's
But
just
there
the,
was
it's,
sixes.
it's the highest number.
Yeah.
So the highest number is 6, so it doesn't matter. If you tie your highest number is
Wait,
6.
Dang. No, the highest number is 6. I think this is great.
Blueberries on that? Huh? Alright, then now do this. Calculate the percentage of wins, and then write how many times player 1 won, proportion, player 2 proportion.
Oh, I guess I could sort portion.
Well.
I mean, yeah.
So.
Oh my, okay, I'm gonna stop.
Jeez.
You won 7 times.
Wait, how is one of yours 8 out of 11? Someone, that's 2 ticks there, that's 12. Okay. Like 8 plus 11.
I know, I was thinking, I was like.
I almost doubled.
Yep.
Wow.
Alright, so write your tally down. How many times did you win?
Or weighted dice.
Oh my gosh.
7, 13.
Yeah.
After you see the prices, hey, look, I want more than
What do you got 8?
Yeah.
Jeez. That's rigged. Big dude. Recount. Stop the count. But-
Weighted dice. Not allowed.
Alright, so you get your percentage. So I think this is. So who was it, Miguel? Were you 65%?
Yes.
Oh, big winner. Okay.
Yep.
So, doing your percentages wise, whatever, you can do it in a proportion. And so, something to note here. So this is just a basic probability model, like who won, what was the percentage. This was player 1, 35% of the time. Player 2, 65% of the time. So like a probability model could just be like 2 outcomes, heads and tails, or it could be like 10, a million different outcomes, and given their probabilities. So the main thing here is that like between these two, right, they add up, so they add to 1. So any probability model that you have, they should all add up to 1. So you got 35%, well that means the other one has to be 65%. Otherwise you did something wrong somewhere. Those don't add up to 1. Those are your only 2 outcomes. Okay, so these are also experimental probabilities. Let's kind of go back to Wednesday. I think it was Wednesday last week. We talked about the probability in the short run is kind of unpredictable, but in the long run, we start reaching our expected probabilities. And a way, something that describes that is called the law of large numbers. When you do many, many trials, your experimental probability starts to approach the theoretical, like flipping a coin. It starts to approach 50-50 after a while. Okay, so this is like kind of short term. Let's get our long term probabilities here. So kind of as the group. So who won more often? Let's see what the rest of the class did. Okay, so let's find the total proportion that player one won for the whole class. So I think there's 1, 2, 3, 4, 5, 6, 7. So 7 times 20. I think there's 140 plays of this game. All right, so let's go through. Let's see. Okay, you said, I think you had 8, right? All right, I'm going to try and do some mental math here. So 8 plus 7, we're at 15. Who is player 1 here?
Oh, we have
7, 22. How many did y'all have?
7.
So 29. How many did y'all have?
8.
29 plus 8 is 37.
We had 6.
Oh no, 43.
8.
51.
51. Got it. All right. 51 out of 140 wins for player 1.
And then you just have to subtract 51 from 100, and that'll be actually never mind. Nope. Forget what I said.
No, you're right.
Right? Yes. Okay. Yes. Yes.
51 from 140 to get that one?
Yeah. That's what I meant.
Yeah, 51 minus 140. Or, so let's do, someone get 51 divided by 140 for me.
That's a big number.
Get your calculator on your phone and go 51 divided by 140.
36.4%.
What is it?
Like 364.
36. Oh, wow. Okay, so 364. All right, so yeah, an easy way to do it, we could get our proportion by doing 51 minus 140, top of my head, I think that's like 89. Is that right? 89 out of 140. And I don't even need to do that in the calculator. Really, to get the difference here, I can just do, I just know I need to do 1 minus
There you go.
36.364 to get this other one, which I believe is, what is that? 6, 3, 6. Is that right?
Yep.
0, 6, 3, 6. All right. So, dang, was that what we expected? Wow.
No.
Rigged.
Explain.
So, 63% to 36%. Huge difference. So, the next time you're deserted, you know, with you and another person, play this little die. Always keep a dice so that you can, you know, rig your odds for you. But, let's talk about one thing here. So, doing this right here is like, let's go over the basic probability word of a complement. So I remember even way back in the day of geometry, we talked basics of like complements, unions, intersections, and probability. And so you've probably seen it again somewhere else. So a complement, so like to get player 2 basically, so player 2 was just equal to 1 minus player 1, basically. Those are which another way to put that is like the not, let's see that. So they should add up to 100. They do. So that's good. All right. So let's look at like what's to explain here with like this 36 to 63%. So one way to help us do these is let's make a probability sample space. Okay. So if I'm doing like flipping a heads and a tails, there's only, let's say I flip a coin twice. There could be heads, 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 tails, tails, heads, tails, tails, and I can see the probabilities listed out. So let's do it here and let's see how many would win. So, yeah, okay, so we're gonna use the table. So let's just list them out. So like this is y'all two, This is like player 1 and player 2 rolling the dice here. Okay, so I'm just gonna list, like this is like you rolling a 1 and a 3. Y'all rolling a 1 and a 4, a 1 and a 5, 1 and a 6. So I'm just gonna go ahead and list all these out real quick here. So that'd be like, whatever. Okay. 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2. Oops, did not mean to do that. Again, I'm just going to make a list of all the sample space.
Why'd you do it like that?
What do you mean?
Which number did you use, like, for the first spot?
Oh, I don't know. I use these as the first
That does
one.
bother me.
I mean, it doesn't matter. You could have listed this as 2, 1.
Oh, okay.
It doesn't matter.
Oh.
It doesn't matter. I'm sorry. I was doing it like this was always the first number in my column.
Oh, I did that backwards.
It's not backwards at all. It's fine.
Well, it's the same number.
Yeah, it's the same thing. You just, you had it somewhere else, so we're good. Alright, so let's find, we listed out this is all the possible outcomes of rolling a dice, 2 dice together. This is every single outcome. So there's 36 different possibilities when you roll a dice. Okay, so let's see. Can I use the highlighter? Yes. Okay, let's highlight, find the probability of player 1 winning. So how many times did player 1 win? That was if the highest number was a 1, 2, 3, or 4.
16.
So that would be 1, 2, 3, 4. I think that would be all of these.
Yeah, 16.
Yeah.
Yeah. So 16. What are we saying? 16 out of 36. Not very good. 16 out of 36. I got that as 4 repeating, so like 44%, basically. 44.4444444. Alright. So that's our theoretical probability. So we look at it and highlighter. Oh yeah, getting fancy. So look at all these possible outcomes of player 2 winning. Looking pretty good for player 2. I'll just write these on the side. So it's like 20 out of 36. So at first glance, it's like, oh, you're giving me 4 and I get 2. But just the fact that anytime a 5 or a 6 pops up with a 1, 2, 3, or 4, it trumps it. So like all these little outcomes right here, kind of 1 away. So these are their theoretical probabilities. This is we had a probability model showing what we had, and I guess we were kind of pretty far off. In our experiment of 140 trials, we got a 36% win percentage. In theory, we should have been about 44%, but that's just the idea that like in the short term, it can be anywhere. It can be high, it can be low, but in the long run, it's going to start approaching this 44% win-loss percentage. Okay, so which was closer to the probability found in number 4A, your group or the classroom? So actually, in this case, I guess this did get closer than this percentage, but actually the thing works. The idea of this question is to talk about, in the long run, the more trials we do, the closer we get to this true percentage. So it's supposed to be that our classroom data together, that classroom experimental data should be starting to approach more closely related to this 44% than your own individual 20 trials. That might not be the case for everybody. Somebody might have had something different. So it's kind of the idea that, so it's probably the classroom data, so more trials means approaching, approaching theoretical probability. So like in the long run, we should get that. In the short term though, the next roll of the dice, I don't know what's going to happen. The next 10 rolls of the dice, I'm not sure. But I know in the long run, player 2 has the advantage. I want to be that person. It doesn't mean player 2 is going to win the banana every time. It just means playing the odds that they have the best chance. Yes, ma'am. Yeah, you can go there. Alright, so we got a sample space. You can always make a sample space of every possible outcome. So kind of for this probability unit, over like formulas and stuff, kind of just throwing out ideas of like how to get probabilities easier. So just like making a sample space of your outcomes, a lot of the times is easier than to just get all the probabilities than anything else. So that's an idea there. So you got theoretical probability, experiment, and kind of approaching that. Okay, so let's see. So kind of the main things here that we're going to talk about is actually going to be in the check your understanding, is where we're actually going to talk about some of the newer stuff. Alright, so yeah, let's talk about these. Okay. Cut this in half. So kind of underneath this in the check your understanding. So probability model. So what it does is it lists, what did I say? Outcomes. That sounds weird, but I'll just go with it anyway. List outcomes. Wow. Smart word. List outcomes and their probabilities. So they must, like, if you have a probability model, it should show all the outcomes and all the probabilities, so all those probabilities must add up to 1. So if they don't, then you don't have all of your data, like something's missing. It's not adding. And so then what that means is, like, your probabilities are always between 0 and 1. You could have 0.1, 0.99, but whatever, they need to add up to 1. Alright, let's talk about complement. So what is the complement? So the complement is the probability of an event not happening. So like the percent chance of rain today, let's make it up, is 10%. So the complement probability of not raining is 90% chance of sunshine, basically. So the way it could be written, let's just say like the event is, I did A. So you could have like A is rain or whatever. And the way it would be written is you have a C in the exponent is the complement. And so that would just be, you just do 1 minus the probability of A happening. So if I want to know the percent chance of not rain, 1 minus the chance of rain is that probability. Yeah.
On like the data tables or charts or whatever, does it have a little C or does it have an
like that.
Yeah.
Uh,
We did last year.
Oh, that was an apostrophe for the compliment last year.
Right?
Typically, I've seen it as C.
Okay.
Yeah. Yeah. Should be C. That's the way I see it in that a lot. Okay. So, whatever it is, pretty basic there. All right, and then the other word that we're going to talk about is are events mutually exclusive? So are these events mutually exclusive or not? So mutually exclusive means the events, whatever event it is, it cannot happen together. It can't happen at the same time. So mutually exclusive events are events that cannot happen together or at the same time. So like that would be like the probability of me rolling one dice and getting a 2 and a 3. Like that's not going to happen. Those are mutually exclusive. Can't happen. Whatever it is. Find the probability that you are a boy and a girl. You can't have both those at the same time, like one or the other. So exclusive events, totally different. Can't happen at the same time. All right, so just some basics. So just going through a few here. So here is a probability model with the number of children in a household and the probability they found in this sample of that happening. Okay. Explain why this is a valid probability model. So all you need to do that. So is it valid is basically there shouldn't be a negative probability. So I'm trying to think of things that are curveball sometimes. Sometimes I'll throw in a negative. You don't have any probabilities over 1, and all of these should add up to 1. So do they add to 1? And I believe the answer is yes, they do. I didn't think about, so yeah, sometimes they'll just list out things and you can't have a negative probability. It'd just be 0. There's no chance of it happening, it's 0. If it's gonna happen every time, it's 1. All right. Explain why these events have one child and have 2 children are mutually exclusive. So, can you have one child and have 2 children at the same time?
No, you have 3.
No.
Yeah, it doesn't make sense. Like if you have 2 children, like you can't just have one. Like those don't happen at the same time. So,
I mean,
like
get rid of one, but
yeah, but then you just have one. If you get rid of one, you just have one. You no
Yeah.
longer have 2. So those you can't have. So cannot have 1 kid and 2 kids at the same time. It's one or the other. Now, like, is it possible for it to not be raining and to be in second period statistics class? Yes, those are not mutually exclusive. Those have plenty of overlap. It doesn't rain and you come to second period a lot, okay?
Like right now.
Exactly. So, a lot of things aren't mutually exclusive. A lot of things in the world are combined together with probabilities, but you can have mutually exclusive where there's no overlap. Alright. Okay, so notation with these. So find the probability that a randomly selected mother has less than 2 children. So find the probability.
Should they have 1 children?
Yeah. So let me just write this out on a way that they might say this. So find the probability that x is less than 2, something like that. Okay. This is not a very scary problem to do. Look at the table. What's the probability of you having less than 2 children?
22.
Yeah, it's not, you just found, right? That's just the probability of 1.
Mm-hmm.
So, not that crazy.
Oh, and then the next one is.
Okay, yeah, find the probability that you have 1 child or, or 2. So the symbol there for that is U for union. So I remember using this in my geometry years as well. So U for union is like a ring, like I'm a union with my wife. Everything is together, we're combined. And so you combine you add those probabilities together. Everything with everything. So what's that? 22, 41?
Yes.
For 63%.
Yes.
And then find the probability that a randomly selected mother does not have 4 or more children. So find the probability of 4 children to the C. So you could do it one of 2 ways. You could do 22 plus 41 plus 24, or you could also just do 1 minus 13%. Sometimes it's easier, like if you're doing the complement and it's just got 1 thing, like it's easier just to do 1 minus that than add up all the others. So is that 87?
Yes.
87%. Okay, so some basic probability. Really, in the nuts and bolts of it, it's not too crazy. It's stuff that you've seen. Where I've seen in the past people lose it is like silly errors, or all of a sudden we get notation and people like don't know how to read it. Like when they give you like an X or an A, they would say up here like X equals number of kids or something like that. Like they'll and just read the table or find the sample space and do the odds for yourself. Alright. Sweet. Okay. On good pace for us to get to what I want to do. Alright. Sweet. I didn't think about this with our math.
Yeah, I was gonna
Yeah,
say.
I was
That's
wondering.
okay.
I was like, how do we do that?
That's alright. I mean, you can, tell me if you can do it or not. So, some people can or can't do the whole like making a U with your tongue. You know what I'm
Oh.
saying?
Yeah.
Like that's what a taco tongue is.
You, what is it?
Do y'all need an example of what that is?
That's just like this, right?
Yeah, you're just literally, some people can't U it up.
Just fold it.
Yeah. Okay, the taco
Can
tongue.
you do it?
Also, some people can't do the evil eyebrow. I was asking my wife, like, can I? Like, can you? And then she tried to do it, and I know my wife can't do it. So, like, I don't know.
I don't
So,
know if I can do it.
all right. So let's see if we can do this.
No.
Yeah, I can do it.
Oh.
So let's think to yourself. Maybe get somebody to check you. Can you do the taco tongue, and can you do
Yes.
like the evil eyebrow? So I'm gonna kind of go person by person, and we're gonna get a little tally here. So like if you don't know if you can do the evil eyebrow, just do it, and someone can tell you real quick if you
No.
can. or
This
not.
right? I don't even know. I think so. Like,
Sure.
I think that's pretty good. Yep, that's pretty good. Yeah. No, my wife was like this.
I can do it.
Like,
I know like what faces do you make.
yeah. All right.
I
All right.
don't.
Let's see here. Okay.
Can't do either.
Okay, that's perfect. Great. We need somebody in that category.
Wait. I mean, I don't usually make that face, but I mean, I can.
You can do the tongue. Can't do the eyebrows.
It's hard to do it almost.
No there. Yes there. Is that right?
Yes.
Yeah.
All right.
Yeah.
Okay, sure.
All right. Here we
Can't do
go.
the clover thing? No. Can you do the clover thing? I think
Yeah.
you can. Yeah. I think
It's
do
so
that.
cool.
Which one?
The I
You-
can't do the tongue.
Okay, that one. All right. Nice.
Oh, I can do both.
Oh yeah.
Okay.
Yeah, you can.
I can't do the evil eyebrow.
That one. Okay.
Only the tongue.
So this one.
Uh-huh.
Okay.
I
Yeah,
can.
I can tongue, but not.
Okay. All right.
I can do both.
Both.
Uh-huh.
Okay. Great.
Both.
Both. All right. Mallory.
I already said.
What,
You
I
can do
didn't-
both.
Okay, I didn't.
Yeah. You can do both.
All right.
I can do the taco thing, but not the eyebrow.
Okay.
Neither.
Neither. All right. That's pretty good. Nice little numbers spread out. Just one in each. Okay, so there's our two-way tables. What is that? 5, 5, 1, 3.
Mm-hmm.
5, 1, 5, 3. All right. So that's a total of what? 10, 4, 14 people. That's right. 6, 8, 14. Okay. All right. So here's the idea on this one: is that a two-way table and a Venn diagram are the exact same thing. If you don't like Venn diagrams, use two-way tables. If you don't like two-way tables, use Venn diagrams. Like, they're both the same thing. And how they kind of work off each other. So, let's see, we got a circle of yes, you can do the taco tongue, yes, you can do the evil eyebrow, and then we've got a circle of both yeses, and then we've also got people who can't do either, and then you've got a box around. So all these people outside of both circles can't do either. So like, there's our 3 there. Yes, you can do evil eyebrow, but no. So that was a 1. Yes, but no eyebrow is 5, and then yes on both is 5. Okay. So let me give you this on like a sentence structure of. We'll look at it later too, but like I told you that 10 people in your class can do the taco tongue and 6 people can do the evil eyebrow, and then I told you that 5 people can do both. So like draw a Venn diagram of that. Okay, so this Venn diagram is not 10, 5, 6. It's 10 altogether, 6 altogether, 5 in the middle. So you do like your 5 first and then get it, and then you still got your number on the outside. And we don't forget about that, because then I also told you there's 14 total people, and so then you have to get that number at the end. Okay. So this is
Oh, you didn't take it. Wait.
This is like a common, especially that little sentence structure of like this makes wrong
That's not the first
Venn
question.
diagrams a lot. But okay, either one. These are just ways to like solve for stuff a little easier if you've got some data. All right. So suppose we randomly chose a student from the class. Find the following probabilities. So what's the probability of getting a yes taco? So I don't have our numbers anymore. So you are gonna have to help me here.
Oh.
Oh,
So-
5.
Yeah.
Oh, wait, 10. Because there's 5.
Oh, yeah.
Okay, yeah. So we had 10 out of
14.
14 of us. So that must mean that no is, I can do that one, 4 out of 14. It's just 1 minus 10 out of 14 is 4
Evil
out of 14.
eyebrow was 1. No, 6. There's 6.
Yes, evil eyebrow is 6 out of 14.
Mm-hmm.
Yes.
So that means we've got, what is that, 8?
8, yeah.
There.
Alright. Okay, the and. So sometimes I'm just gonna go for notation here. You don't have to write this, but like, let's say that A is that you can do taco tongue, and the and is listed as, and it looks like an N, and that's intersection. Like, where do these collide together? So where do these intersect? And then let's say that B is evil eyebrow. So this one would be for that thing right there. Like, yes, taco tongue, yes, evil eyebrow. So what's the probability of those intersecting together out of everybody? I think that was 5, right? Like 5 people could do both out of 14. So you need to be able to read a two-way table and a Venn diagram, both of them. Okay, let me go for like this notation. This would be the probability of A intersection B complement, because there was no evil eyebrow. That's like the notation of it. So this is yes evil eyebrow, and this is not yes, which is the word no in English. So, I don't know what that is because I don't have our table. So what's that?
5 out of 14.
Okay. 5 out of 14. Okay. So this one, with what I've done over here, let's just keep going for the notation. I'll just try and write it small here. So evil eyebrow I listed as B over here. So technically this one is probability of B intersection A complement. Just they switched the statements around. Which, was that 1 or 3?
Yes.
That was the 1. Alright. And then this one is the probability of no taco tongue, so I think that was A for me. So A complement, intersection with no evil eyebrow B.
There's 3 out of 14.
Alright, sweet. Okay. So, notations are a killer sometimes on some easier things, just because we start getting confused on them. But we'll get some practice on it and look at them, should be able to get it. Okay, so that's our probabilities. Okay, so let's do this one. Suppose that we did this. So what's the probability of yes, evil eyebrow? Was that 10, I think?
No, 6.
Oh, okay. 6 out of 14, so then that one was 8 out of 14. Okay. So, let's talk about this real quick. Are these mutually exclusive or not? So,
Yes, because you
yeah.
can't have both.
You can't do both at the same time. You can either do it or you
Yeah.
can't. Like, you can't just all of a sudden just do it. So these are, so maybe I'll say, events are mutually exclusive. Okay, so how do we calculate the probability of yes, evil eyebrow, or no evil eyebrow? That's kind of weird. So these events are mutually exclusive. And how do we get yes or no? So the probability of yes or no, or is you just add them together. And since they're mutually exclusive, there's no overlap. I'm going to add 6 out of 14, plus 8 out of 14. Like, there's no overlap between those. And since we talked, those are only 2 events allowed here, or around here, it's 100% odds you're going to get one or the other. So you're either yes or no. You're 100%. Like, the odds are 100%. What I want to focus on here is we're going to look at the distinction between mutually exclusive and this one down here that's not. So on these mutually exclusive events, all we did is add the probability. An or statement is combine them together, just add them. Which, for me personally, I do best with like the Venn diagram. So I would say yes or no, and I would look at it as like you're either yes, evil eyebrow, or you're, so that would be like yes or you're no, and then at that point you circle the whole table and you're 14 out of 14. Do it either way. Okay, so let's look at this. So we did that. Suppose we randomly chose these students. So what's the probability of a yes taco tongue? Was that
10.
Okay, yeah, 10 out of 14. That's right. So was evil eyebrow, was it 6?
Yes.
Okay, so yes, evil eyebrow is 6 out of 14. Okay, and these events are not mutually exclusive. You could be yes to both of those. So these are not mutually exclusive. So what that's going to do is that's going to impact our yes or yes. So probability of A union B So yes or no. So what I'm going to do when I'm adding, or is an adding thing, I add the two events together. So I'm going to add 10 over 14 plus 6 over 14 to get 16 out of 14 odds. Coach, I'm giving 110%. Like, that's me. But this goes over 14. So the reason is because then there's some sort of spot where these happen together. So not mutually exclusive. These happen together. So what I have to do is I have to subtract where those happen together. So is that 5?
Yes.
Okay, so I have to subtract 5 out of 14.
So 11 out of 14.
So 11 out of 14, right? So yes, 11 out of 14, whatever percent chance that is, but fraction, same thing, it's fine. So there's our answer. But the main thing here is if the events are mutually exclusive, you just simply add them together. Like, I'm trying to think of, like, let's go for like a deck of cards. What's the probability of you pulling out a 2 or a 3 in a deck of cards? That would be 4 out of 52 plus 4 out of 52 cards. But like, if they're mutually exclusive, what's the probability of you choosing a 2 out of a deck of cards or a red out of a deck of cards? Those can happen at the same time, so you'd have to subtract the 2 cards that are both 2 and red. So when they're not mutually exclusive, you have to subtract the probability of those together. Okay. So it's little things, little details that make the mistakes here in these kind of basic ones. Reading the questions. If they can happen together, you have to subtract the overlap with them, whatever the odds of those happening together were. Alright, so the or, adding them. Yeah, let's see, we'll talk about the and on the other one, right? Oh, that was at the top. Okay. Alright, so what that is I'm trying to think. So I don't even like to use the formulas on here very often. Yeah, so there's a formula on the formula sheet that has probability rules. It says do the probability of A union B is A plus B minus A and B. But just the general rule is like, so let's go for this. So this is like our addition rule. So this is when you're doing a union an or statement. So the probability of A or B equals, so it just depends. Let's go for like an offshoot here. So if they are mutually exclusive, so let's go for that one. I'm gonna say mut x, because that totally makes sense. For those of y'all that are listening at 2 times speed on YouTube, fast forward, there we go. So you got just the probability of A plus the probability of B, and that's it. If they're mutually exclusive, there is nothing to subtract over. If they're not mutually exclusive, you have to add those 2 probabilities, but then subtract. So let's go for, you have to minus, and basically it is the overlap, which is where those happen together. So like the probability of A and B. Just where do those overlap together? Alright. And then just another thing, so like, oops, that, oh well, this will work. Just the distinction with like a two-way table and a Venn diagram. So let's say, I'm going to go for A. So I just want to get the connection here. Okay. So like these can be anything, whatever we want to call A and whatever we want to call B. Passing AP statistics and passing IB bio, whatever. So like here's that on. I'm just gonna give them numbers. So like the number 1, the number 2, the number 3. Beautiful color coordination. I'm just on top of my game. Okay. Alright, so the probability of both of those passing together or whatever is those happening together right there. Like that's that number, same number. Okay, so let's say that this is like A and this is B. So then here's the number 2. Oh wait, yep, that's right. I was about to say I did that wrong. Here's the number 3. And then the whole entire outside of the circles is the 4th probability. And so another thing to note, right, though, is that the probability of A happening is not just 2 and it's not just 1, it's like 1 and 2 together. The probability of B is equal to 1 and 3 together. So like if I gave you, here's the percent chance of A, here's the percent chance of B, and then you have to come up here and do it. Kind of getting the differences. Sweet. Okay. So, I didn't add it. All right, what I want to do is actually, instead of the check your understanding, we're going to do some extra problems here on this little quiz. It's not a quiz, it's just the paper I'm using.
What's your playing on your computer? That's so funny.
Okay, so these are just, I like the Venn diagram on this, that's why I'm doing it instead of the check your understanding. Check your understandings are always good, but just gonna do this. So let me see here. All right. Oops. Stop. Okay. Yeah, we got plenty of time. We might as well just go for it all here. Okay. So this first one, not too bad. And these are like legitimate, could be problems that we shouldn't get wrong. Alright, so here is a probability model. We've got our listed outcomes, what education do you have, and the probability of U.S. residents over the age 25 in this survey. Here's their probabilities that we got. Alright, what's the probability that a randomly selected person has a graduate or professional degree? Give me that below. So, what's the probability of, so, like, technically, I don't know, I could say like, so graduate or prof, whatever. Okay, if we're going for notation wise. This problem, you don't have to write the notation. but I think it's probably a good habit that we need to do. So I could point out that those are mutually exclusive people. Oh wait, oops. I didn't
You're
even
just
do
trying to
that.
figure out the question.
Yeah, I just
Yeah.
need to, those are actually
Yeah.
one thing. I'm just not reading the full thing there. Alright, so not even the part of that there. We're fine. Okay, so how do we get it?
Can you add everything up together and subtract it by 1?
Yeah, so whatever these are.
That's like 7 something, maybe, or 8.
What is that? That's 71 added together. 71, so is it 10, I think?
Yeah, it's 10.
Yeah.
Okay, 10%. So 10%. So yes, 1 minus 0.2, 22, 29, 19. 10%. Okay. Alright, what's the probability that a randomly selected person has at least a high school diploma? So, on this case, again, this isn't that bad. They're not that big of numbers. It's not that big. At least a high school diploma is all of these people there. But basically, at least is talking about greater than high school diploma. It's basically just 1 minus the probability. So you could do it either 1 minus the probability of like high school or no high school, or you can just add them all up. So either way, it should be 80%, whatever way you do it, hopefully. So, in math, there's lots of different ways to do different problems. Okay, here we go. I like this one. Oops, I just took a screenshot of that. Nice little picture. Okay, there are 35 students in Miss Ortiz's pre-cal class. One day, 24 students turned in their homework and 14 turned in test corrections. 8 of them did both. Suppose this was a random selection of students. So let's make a Venn diagram. H is going to be homework, C is going to be test corrections. So let's make a Venn diagram of those. So H, C, and so they did do them together. So they're not mutually exclusive. So that's why I overlapped them. If they couldn't happen together, there shouldn't be an overlap, but they could happen together. All right. So, what are my fill-ins? I should have 1, 2, 3, 4 numbers listed, and they should all add up to 35.
8 should be in the middle.
Okay, yeah, so I got 8. 8 are both.
And
That's
then
always a good start.
You do 35 minus 24 to, like, no, you do,
24 minus 8.
yeah, there you go.
Okay, yeah, so 24 total students in this blue circle. So 24 minus 8, what is that, 16?
Yeah.
Okay. The whole blue circle adds up to 24. This entire red circle should add up to 14.
14 minus
6. You know, those are one of those things, like 8 plus 6. What's another one that always gets me? Like, I always, like, pause at my 8s. I don't know why.
80. I always pause for pause.
Not good. Okay, and then, what about our last number?
Yes.
5. So you added all those up. 22. Yeah. So 22 plus 8 is 30. So all of these added together are 30. Should be 35. So 5 students just went home and did nothing. Didn't learn anything. Or actually, you know, they really did it that night. I'm telling you, I did it, but I left it. Okay, so 5. Okay, what's the probability that a randomly chosen student turned in neither homework nor test corrections? So we just calculated that.
Yeah.
I think that was 5 out of 35. Which I have no idea what that probability is. Is that 1 out of 7? I don't know that.
Yeah.
14%? 10? No. What's again? What's 5?
0.14.
That's it? Just 0.14?
Yeah.
Oh. Are y'all impressed or not? I totally guessed 14%. I don't have, that's not my key. Hey, that's pretty good. Okay. You know.
Because your mouth.
Genius. Wow. Okay. Such useful information that I use all the time. Alright. Let's see. Might as well finish this out. Didn't take a picture that time. It's good. Okay. 120 subjects in a survey. Do you exercise? And what kind of car do you drive? Okay. So list 2 mutually exclusive events. There's a bunch. What are 2 events that are happening that cannot happen together?
Exercising and not exercising.
Okay, yeah. So you could say yes, yes, exercise, and no. Yep. Oops. Yep. Great handwriting. Another example would be like you drive a truck and an SUV. Like those are mutually exclusive. Or you drive an SUV and a sedan. Okay. It's movie season. What's the probability that the person selected drives an SUV?
39 out of 120.
Yep. 39 out of 120. Not too bad. Almost. What's 40 over 120? Almost 33% chance. Like 31. What is it? 0.3 something?
Repeating.
Oh, it's just 33? Well,
I think it repeats.
Really? I thought that would be 40 over 120.
Oh, I thought you were asking
No, what's 39 over 120? 2.5?
Yeah.
Okay. There's no other decimals after 5? Oh, cool, yeah. So generally with decimals, going to 3 is a nice number on that. Because what that really is that's 32.5%. So that's kind of nice to see over 33%. But there's no set rule on rounding. You could round to 2 or 3 decimal places. What's the probability a person selected drives either a sedan or a truck?
Isn't that just 45 plus 36?
Yeah, so these are mutually exclusive events, right? So just add them together. 45. Technically 45 over 120 plus 36 over 120. And there's no overlap. There's no second guessings. So let's say it's 81. So that's something like probably about 68. Something, 6 something. It's a decimal.
675.
Ah, genius. Okay. Alright. And last one. What's the probability drives a truck or exercises 4 more times? So yes to exercise. So drives a truck was what? I don't have
36.
36.
36 out of 120 plus 52. But, so these are not mutually exclusive. So, where's the overlap?
12.
Only 12 people? Okay. So 36 plus 52, but take away the 12 where there's combined, what's that, 76 out of 120. some sort of decimal in places. Alright, sweet. So pretty basic probabilities, but I can't tell you how many mistakes are made on them. And so being careful, being diligent, writing out rules, using sample spaces, using tables, yeah, just taking your time, thinking about if there's overlap or if there's no overlap, and the differences. All right, sweet. So on Friday, we're gonna do some more probability, and we'll go from there. All right, ready, break. Great job.